Hello my wonderful students, you're welcome to yet another transformative class on waves under physics. Alright, I'm sure that you're enjoying our classes so far, and in our last class we introduced the subject of waves in physics, and we said that waves are disturbances or vibrations that travel in a medium, and in that course transfers energy from one point to another without permanently displacing the medium. All right, so today we're going to be talking about properties of waves. So in case you have not watched the last video lesson, go back to the video lesson and watch it, and also subscribe to the channel so that you don't miss out on upcoming ones. In this way you have the foundational knowledge of this particular topic. All right, so today we're talking about the properties of waves. What are the properties of waves? What properties does waves exhibit? The first one is reflection, second is refraction, third is diffraction, fourth is interference, and fifth is polarization. All right, so what is reflection? We're going to take them one after the other and explain the phenomena that follows each one. All right, so what is reflection? Have you ever shouted in a very large room and you heard your voice? That was an echo. What happened was a reflection. All right, then have you actually flashlight on a glass, then you saw the light bouncing back? Right, even all these things like shadows, eclipse, they are all phenomena that are associated with reflection in physics. All right, so what is reflection? Reflection is the bouncing back of waves when they hit obstacles. They hit obstacles, so they bounce back. So what is reflection? Reflection is the bouncing back of waves when they hit obstacles. All right, so what is reflection according to this diagram here? So this is a blank surface or an obstacle. All right, this could be a wall, a mirror, or some other thing, or a wall. So this is a plain surface. All right, we label this as plain surface. Plain surface. All right, so this is a wave coming. It can be a light wave or anything, so we call it incidence wave. It can be sound, it can also be light. All right, so we call this the normal. So the normal is an imaginary line. If you watch, the line is dotted. It's an imaginary line. This is angle 90. All right, an imaginary line that is drawn perpendicularly to the plane surface. All right, and usually drawn between the incident and the reflected. So this is the reflected. If it is light waves we're talking about, we call it the reflected ray. All right, so this is the reflected. So what you should know is that the angle between the incident and the normal is the same thing. It's the same thing as the angle between the reflected and the normal. All right, so the angle, if the angle between the incident and the normal is the same as the angle between the normal and the reflected. So if this is 60 degrees, this will also be 60 degrees. Are we together? All right, so you understand this? The incident wave, remember this is the arrow. The arrow is pointing towards the side. Then the reflected, the arrow is also pointing like this. If you point the arrow like this, maybe like this, you are already fading. All right, so the right way is to point it opposite to this. All right, because it is bouncing off. All right, so we have the laws of reflection. So the first is that the angle of incidence, we now call this the angle of incidence, and this is the angle of reflection. The angle of incidence is equal to the angle of reflection. All right, you can put that down. The two laws of reflection, that the angle of incidence is equal to the angle of reflection. All right, or incident angle is equal to reflected angle or reflection angle. All right, so the second one is that the incident wave or the incident ray, the normal and the reflected, all right, they are at the same plane surface, all right, they are on the same plane surface, or they lie on the same plane. The incident wave or the incident ray, the normal and the reflected, they lie on the same plane. You can see that all of them are lying on the same plane. So this is for reflection. So we can see the application of reflection in eclipses, in shadows and other natural phenomena that we see in day-to-day, even echo, the echoing of sound. All right, so we are going to demonstrate the reflection of sound and light waves. So for sound waves, just to stay in an open place, like in a room, in an empty room, then you shout. If you shout, you're going to hear your voice back, and that is the reflection. That's simply it. But for light wave, you are going to flash a light, let's say on a board, then you see the reflection. All right, okay, I'm going to show you an example with my LED light, the LED light I'm using to shoot this video. All right, so you can see this LED light now. I'll show you around. You can see this LED light, right? You can see this LED light. The ray is incident like this on this whiteboard. All right, and obviously you can see the reflection here. You can see the reflection here. All right, there's a reflection here. Do you understand? So that is an application. If I take this LED light closer, you see the reflection very well. All right, yeah, so that's another application of light waves. Sorry, reflection of light waves. All right, so I think it's a bit clearer now. Okay, so we can go further to talk about refraction of waves. Okay, refraction of waves. I'm gonna draw another diagram, of course. So this one is going to be like this. So this is the normal, or we can make it dotted still. It's an imaginary line, all right? Then this is the plane surface. The plane surface. It can be water if it's a water medium, all right? So this is the incident. The incident wave. Incident, and this is of course the angle of incidence. All right, so this is the reflected. Remember, the arrow will point like this. All right, so of course it will be the refracted, not reflected now, refracted, because we're talking about refraction now. It will be the refracted ray, or the refracted wave. The refracted. All right. So I don't know if you've actually placed a stick or a pen in a bowl of water, then you see the pen bending. Okay, that is an application of refraction. All right. You can just try it out in your kitchen or in your house. Just get a bowl of water, then put a broom or a stick or just your pen. You see that the pen bended, it will become shorter. All right, that is a refraction. All right. So refraction is the bending away, the change in speed, the change in direction of a wave as it passes from one medium to another. And actually it is from a less dense medium to a denser medium, or even vice versa. All right. So this medium, this is another medium, this is another medium. So this, we call this medium 1, and this is medium 2. It can be air and water. All right, maybe you are placing a stick in water, the top is air, so that is water. All right, it can still be air and maybe alcohol or something else, maybe air and glass. This is the case of light or something. Okay, so you're going to consider an incident ray hitting the plane surface and makes an angle with the normal, then it refracts. All right, so we have two laws of refraction as well. We have two laws of refraction as well, and the first one is that the sine of the angle of incidence, the sine of the angle of incidence, that's sine I, divided by the sine of the angle of refraction, all right, is equal to the refractive index. The refractive index is usually noted as n, refractive index. Refractive refractive index. I know it's the refractive index of medium 1 and medium 2, so we write 1 and 2. All right, that is the refractive index. So, and this is called Snell's law. Snell's law. So, in case in a Snell examination like waec and neco, they ask you, or even jump, what is Snell's law? This is the mathematical expression. You can state it as the refractive index is equal to the ratio of the sine of the angle of incidence to the sine of the angle of refraction. All right, so that is Snell's law. So the second law of refraction is that the angle of the incident ray or incident wave, all right, the refracted wave and the normal, they lie at the same plane surface. All of them are convergent at the same plane surface. Do you understand? All right, and obviously you see that this angle is not the same thing with this. All right, it's not the same thing. All right, so you may not say that the angle of incidence is equal to the angle of refraction. All right, so we can still make some deductions from this. Refractive index, all right, n is equal to v1 over v2. Remember, I say that refraction is the change in the speed. So this is the wave speed, all right, in the speed, in the direction of a particular wave as it passes through two mediums of different densities. All right, so this is n equal to v1 over v2. That is the speed of the wave in the first medium over the speed of the wave in the second medium. And from the relationship between wavelength and wave speed, we know that v is equal to f lambda, right? V equal to f lambda. But note this in refraction, that the frequency is constant. There is no change in frequency. In refraction, there is no change in frequency. So the frequency of that particular wave when it is in medium 1 is the same frequency when it is in medium 2. All right, so if v is equal to f lambda, so we have that this is equal to f lambda 1 over f lambda 2, because they have the same frequency, so we can cancel out. We can cancel this out, cancel this out. So we have that 1 and 2 is equal to lambda 1 over lambda 2. That is the wavelength of the wave in medium 1 over the wavelength of the wave in medium 2. Do you understand? So we can make a general statement. The refractive index is equal to v1 over v2 is also equal to lambda 1 over lambda 2. All right. So you see that this is very, very simple. So in case in calculations you can be given any of the values, you know how to compute them to get your refractive index. All right. So in subsequent classes we'll be doing some calculations on refractive index. All right, and under refraction. All right, there are a lot of questions from JAMP, WAEC, and NECO under this particular topic. All right. So the next property of wave we're going to talk about briefly is the diffraction. Diffraction is the ability of waves to pass through small openings. All right. It is the ability of waves to pass through small openings. It's the ability of waves to pass through small openings. I'm going to exemplify it. So you can see this narrow slit. This wave will actually pass through it. That is diffraction. So waves have a way of passing through narrow crevices or narrow openings. For example, they open it through a door. You see light passing through it. You can see the movement of the ray of the light outside the door. Do you understand? So what happens is what diffraction. This is when we have a wide slit, or we can have a narrow slit. What will happen? Remember, this is a parallel wave front. This is the wave front, and it is parallel. All right, it is square. All right, so it moves and the shape is not distorted. But what if we have a smaller space? What if we have a smaller space? We will have a different experience. All right, so we're going to have a different experience because they'll be struggling to pass through this narrow slit. What happens is that it will become circular. The resultant wave will become what? Circular. All right. So when we have a parallel wave front approaching and we have a narrow slit, what happens is that it becomes circular. It gives off circular wave front as a result. All right. So the next one I'm going to talk about is interference. Interference is another simple one, and I guess you're going to enjoy it. All right. Interference or superposition. All right. It's called interference or superposition. It is when waves superpose upon each other. All right. As they move, they superpose on each other. I'm looking for a diagram that can help us understand it better. Okay, let's say we have this. They superpose on each other. So we have this. This is a transverse wave. Alright. And we have this. These are a second wave. The second wave. And the third wave. So you can guess what is happening. These waves are superposing each other. Alright, they are interfering with each other. Alright, so this is called what? Constructive interference. We have two types of interference. We have constructive and destructive interference. So what happens is that the wave, the resultant effect of the wave, we have a bigger wave. Alright, so it's interfering and you see it is coming down. We have more. The wave is increasing. Alright, but this is for constructive. Alright, but we have another case, destructive interference, in which the interference brings about the cancelling out of all the waves. From the name destructive, it destroys the wave. This is a wave. This is another wave. It comes in the opposite direction. So up to 0, the end is 0. It will cancel. Alright? It will cancel. So this is what destructive interference. Alright? So that is so where this particular two waves meet together is called the node. And where they are apart from each other is called the antinode. Alright? The antinode. Where they are apart from each other is the antinode. And the way they meet together is called the node. Alright, so lastly, we're going to talk about polarization. Polarization is a very simple one too. So polarization is the ability of a wave to travel in one plane. In one plane, the ability of a wave to travel in one plane. Alright? This wave is vibrating in one plane. So I'm going to give you a simple diagram. So polarization is the ability of a wave to travel in one plane. Alright? So you can see this unpolarized light, okay? Unpolarized wave, or basically light, because light is one of the waves that can be polarized. In fact, only transverse waves can be plane polarized. Alright? Longitudinal waves like sound waves cannot be polarized. Okay, they can't be plane polarized. Okay, so as this wave comes, this is a polaroid. Alright, we call this a polaroid. You can call this P, then we call this Q, a polaroid. So when it passes through this, it becomes polarized. Because plane polarized, you can see, it becomes plane polarized. So when it passes through this, it also becomes plane polarized. Alright, you can see a gap here. Alright, a gap here, a square gap. Alright, or rectangular letter. Rectangular. So these are polarized waves. But there's something amazing that happens, which is that when you rotate this, remember this is at angle 90 to this, they are on the same angle. Alright, so when you, okay, let me say this is just like this. Let's say two perpendicular entrances in a hall, and this is the first door. You can see something like this. Something like this. This is how this thing is. So you can see that there's angle 90 here, 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 there's angle 90 here. Alright, this is what is happening. Alright? But when you rotate this, whether like this or like this, alright? Let's say we rotate Polaroid, Q, and this shape eventually becomes like this. You bend it. Alright, instead of being like this, it's now like this. Alright, when we rotate it to become like this, you see that the angle has changed. That angle 90 has been altered. So the wave will stop here. Then there will be no polarization again. So no polarized waves. Alright. So this simply demonstrates that light are transverse waves. If actually the wave here is light, it shows us that light is a transverse wave. It's a transverse wave. That it depends on this angle 90, that it must vibrate along angle 90. Alright? Angle 90 to the source of the vibration. The vibration is coming like this, so it must be angle 90. This thing must be angle 90. Because angle 90 has been altered. That is why it is no longer polarized. Do we understand? So that is polarization for you. So I don't know if you have any questions. You can relate them in the comment section and I'll be glad to answer. So do well to subscribe to this channel as you anticipate several calculations across each of these. Alright, so next we're going to be talking about light waves, application of light waves, sound waves, electromagnetic waves. Oh, you can't wait for that. Thank you and God bless you. Bye.